Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing OSPF, where we will review OSPF concepts, configurations, and troubleshooting in Junos. In this lesson, we're reviewing one of the fundamental underlying processes of OSPF, the neighbor relationship formation process. Most dynamic routing protocols have the concept of neighbor relationships or adjacencies. This concept is one of establishing a relationship with another device such that the two devices agree on certain attributes regarding the sharing of network reachability information or routing information. Many times, though, the term neighbor or neighboring router will be used to describe a router connected to the same segment, which also speaks OSPF, where the term adjacency will be used to describe the relationship that's then formed. This is especially important in link state routing protocols. As we discussed in another lesson, the link state database among all OSPF-speaking routers in an OSPF area must be identical for the OSPF system to route data traffic appropriately. To ensure the LSDB is identical, neighbor relationships are formed, allowing each router to have an awareness of all other directly connected OSPF-speaking routers, such that it may send and expect to receive routing information to and from them. OSPF-speaking routers won't just form a relationship with any old router, though. A certain set of conditions must be present. Let's start off by reviewing what those conditions are. In order for OSPF-speaking routers to form a neighbor relationship, they must exchange OSPF hello packets. As we described in a previous lesson, the OSPF hello packet contains these fields. Since hello packets are sent to the multicast destination address 224.0.0.5, the well-known address for all OSPF routers, any OSPF-speaking router on the subnet will receive the hello packet. Because of this, OSPF routers will automatically discover one another on a broadcast, point-to-point, or non-broadcast multi-access link. OSPF has a concept of partial neighbor adjacencies, which are described by the state within the OSPF state machine where the neighbor relationship will stall. This is called a two-way neighbor, as opposed to a full neighbor. Two-way neighbors stop the neighbor relationship formation process before the exchange of any database information. The neighbor relationship is formed and both routers have validated that the fields in one another's hello packets match, and the routers list one another as neighbors in their hello packets. However, they do not exchange any routing information. They are only aware of each other. We'll go into this concept and where it comes up in OSPF topologies in a later lesson. As we've mentioned a few times, the OSPF hello packet contains these fields, and 4 of them must match with a neighboring router for an adjacency or neighbor relationship to form. These are the network mask of the interface originating the hello packet, the configured hello and dead intervals for how often the router will send the hello packets, and how long it will wait before considering an established neighbor as dead. And finally, the options field must match, which contains flags for the capabilities of the advertising router. Since we now know what fields must match for a neighbor relationship to form between two OSPF-speaking routers, let's take a closer look at the neighbor relationship formation process and the steps involved. The parameters that must match are selected to ensure that the routers can reliably forward data plane traffic. And it's during the neighbor relationship formation process that the link state database of the two routers are synchronized. In the diagram here, we have the states that OSPF-speaking routers must pass through and the packets that are exchanged to form an OSPF neighbor relationship. In the first step here, we see that both routers would see the neighbor relationship as being down initially. If the neighbors are being dynamically discovered, as is common for OSPF deployments, then in reality, the two routers at this point are simply unaware of one another. When R2 receives the hello packet from R1 and confirms the four properties match, it will add R1's interface IP address to the list of neighbors in its own hello packet that will be sent back. At this point, R2 will show R1 as a neighbor and will be in the init state, as two-way communication has not been confirmed yet. When R1 receives R2's hello packet and sees its own IP address in the list of neighbors, and presumably the four properties still match, it knows that two-way communication is established. R1 will show R2 as a neighbor and will be in the two-way state. R1 will also add R2's interface IP address to its own list of neighbors in the future hello packets. Once R2 receives the hello packet with its own IP listed as a neighbor, it will transition its R1 neighborship to the two-way state. At this point, if a full neighbor relationship is to be established, then we will start the database description exchange. Between the two routers, the one with the highest router ID, or RID, will begin the exchange. This is also called the master router of the DBD exchange process. In this case, it's R2. When the database description packet exchange begins, the master will continue to show the other router as being in a two-way neighborship state until a response is received. On receipt of the DBD packets, the routers transition the neighbor relationship to the XStart state, or exchange start. This is because the interface MTU has not yet been verified for each node, as the field is only included in the DBD packet. Once a DBD packet has been received on both nodes and the interface MTU is verified, then the neighbors are in the exchange state. The exchange state is when the full database description is exchanged between the two routers. Once the exchange of database descriptions is complete, then the routers proceed to send one another LSRs and LSUs to shore up one another's LSDBs. This is the loading state. Once the exchange of LSRs and LSUs is complete, the neighbor relationships are in the full state. Now that we understand the process an OSPF speaking router goes through to form an adjacency, I want to circle back a bit to the difference between a neighboring router and an adjacent router, and briefly touch on where that difference would appear. As we mentioned at the beginning of this lesson, a neighboring router is one which resides on the same subnet or broadcast domain and speaks OSPF. A neighboring router, when talking about OSPF, will not exchange routing information, though. These routers see the hello packets and agree on the four parameters, though they will stop at the two-way neighbor state. An adjacent router, however, has proceeded with the database synchronization process and is in a full neighbor state. On a broadcast link, as is typical in our enterprise environments, this full neighbor state will only be seen with the DR and BDR on the link. We'll cover the DR and BDR function in OSPF in a future lesson. As we see in the diagram, we have 5 routers, all connected to the same broadcast segment and speaking OSPF. The 3 non-DR or BDR routers on the bottom will simply form relationships with one another and stay in the two-way state. This indicates they are aware of one another, though they will not perform a database synchronization process, and nor will they exchange LSRs or LSUs in the future. The routers will all form full adjacencies with both the DR and BDR, however. Additionally, the DR and BDR will form full adjacencies with one another. This function in OSPF is primarily in place to limit the unnecessary flooding of LSUs on the segment. which was an important feature back in the times when OSPF was developed, and link speeds were much slower than they are today. This last note here references a configuration that's available in OSPF of declaring a particular interface or link as a point-to-point link. This should only be done on interfaces where two nodes are present. In this case, a DR and BDR will not be present on the link, and the two OSPF-speaking routers will form full adjacencies with one another. Now that we've covered most of OSPF theory, let's take a brief look at how we configure a very basic OSPF deployment and how to monitor our OSPF neighbors. Configuring OSPF can be very simple. The only configuration necessary is for an area ID to be specified and an interface added to the area, and that's it. In this example configuration, we see that Area 0 has been configured. Areas are expressed in Junos in the same format as an IPv4 address, as this is a 32-bit field. As we'll see in a future lesson, Area 0 is a required area if multiple areas are to be configured in your OSPF domain. Within the Area 0 configuration, we have added the interface GE002.0. Note that this is the logical interface unit 0 rather than the physical interface, and must have the INET family with an IPv4 address configured. We've also configured the interface with a priority value. The priority value is only used in the DR and BDR election process, which we'll review in another lesson in this section. At this time, once the interface and area configuration are complete, the configured interface will begin originating hello packets with the default timer values. If any other compatible OSPF-speaking routers are present on the broadcast domain, then a neighbor relationship will be formed. At the bottom, we see that a RID may be specified manually by using the Set Routing Options Router ID configuration command. A router ID configuration is not required, though. Junos will automatically set the router ID to the highest loopback IP address if one is configured, or the highest interface IP address if a loopback interface is not configured. Finally, let's take a look at how our OSPF neighbors are viewed and displayed in Junos. We can view a list of the OSPF neighbors that the local router is aware of using the Show OSPF Neighbors command. The far left column displays the interface IP address of each neighbor on the segment where they are seen. The next column, Interface, shows us the Layer 3 interface on the local device where this neighbor is seen. In this case, we only have a single interface configured for OSPF on this router, so all three of our neighbors are appearing on that one interface. The next column gives us the neighborship formation state. As we see, we have two full neighbors and one which is only in the two-way state. Since this is a broadcast segment, the routers with the highest configured interface priority value will become the DR and BDR, and therefore form full adjacencies with all other OSPF-speaking routers on the segment. The next column to the left shows us the router ID of each of the neighbors seen. As mentioned earlier, this can be a loopback address configured on the router, a manually specified value, or an IP address configured on an interface. The PRI column displays the priority of the neighboring router's interface. The highest priority values will become the DR and BDR on a broadcast segment, as we see that is the case here. The neighbors with the priority values of 255 and 254 have formed full adjacencies, and the one with a priority value of 128 has only formed a two-way neighborship, which would be expected if the top two are the DR and BDR for the segment. Finally, the dead column displays a countdown timer in seconds. This is how many seconds remain before the neighboring router is considered dead, if another hello packet is not received. When a new hello packet is received, the timer will reset to the configured dead interval and begin counting down once again. I appreciate you working through this lesson with me to cover the OSPF neighbor and adjacency formation process in detail. I hope that this lesson has been informative for you, and I would like to thank you for viewing.